Yeah. So, so this is the question. We are looking at question number 17, which has a series motor. So let's begin by first drawing it, and then from there we will go forward. So a series motor looks like this. Since it is a motor, we need to give electrical supply. So this is the series field winding, and this is the armature winding resistance just showed outside. We can keep it like a resistance symbol, and then this is the armature. So let's go to the data. 250 volt and 0.35 and field is 0.45. Okay, so let's put that here. I hope these numbers are correct. Sorry. Current required to develop torque of 70 Newton meters at 1800 rpm. So the motor output is mechanical. So torque is 70 Newton meters, and sorry, N should be capital. And speed of 11. How much was that? RPM. Okay. So this is the given data. The question is find what is the current. So let us try to find that. So right away I can say the output power is torque into omega. So torque is 70 Newton meters multiplied by 1080 revolutions per minute RPM. So divide by 60. So you get revolutions per second. And in one revolution there are 2 pi radians, so multiply by 2 pi radians, so you will get uh, the output power. Okay, so this will be in watts. So so can someone help me with the calculation? So yeah, how much is that? So I pull out my own calculator also. Still no answer. 70 into 1080 into 2 into pi. So I'm getting 7927. Is that correct? Okay. I think 3.145 I came. 3.1415, right? So I just made a third decimal there. So 79. Okay. So 7913 watts, I'll take it. Okay. So this much of power has come at the output. Okay. So the question is, what is the current here? Okay. So we need to find what is the input power, right? So now there will be some copper losses also here, and all the things, right? So I think some data is missing. Any ideas what to do next? I think we may have to make it like an equation or what. So I got the output power. Let's read the question once again. Calculate the current required to develop a torque of. Okay. See here, what you can do. Let's say there is some current here, and from that I can find out what is the output power. So let's assume the current is I. Okay, so I into 250 is your input power, then losses. So only copper losses I will take. So I square multiplied by 0.45 plus 0.35, right? Okay, and then assuming the like neglecting the rotational losses, so my output power already I have mentioned here, right? So these three together, so we have a constant and we have a term with power 1 and we have a term with power 2, and these three are related, right? So input is nothing but output plus losses. Okay, so uh, this I into 250 is nothing but these two 7913 plus this losses. Here I'm ignoring. So I think this is zero point 0.8, right? 4 plus 3 is 7. Yeah. So if I ignore the rotational losses here, so I got equations. I can find the I. So minus. Okay, let's make this 0. So it will become minus I into 250. Okay. So this is A, this is B, and this is C. So minus already is minus here is there. So it will become plus 250 plus or minus square root of 250 square minus 4 into zero point 0.8 into 7913 divided by 2 into zero point 0.8. So can again you have to help me with the calculation or let me try it here. You're following, right, what I'm trying to do? So 250 square minus 4 into 8 into 7913, is that 7913 the output power? Yeah. So this one I need to square root, and it's saying 192. So let us take the minus sign, and 250 is already there. So this is the numerator minus b minus square root whole we have to divide by 2a. 2 into 0 0.8. Okay. So I'm getting 35.739 as the answer by taking the minus sign. So is it there in the options? So the finally the current 74 amperes. So let's look at the choices. So looks like B is the answer. Although I should have made the what you call more decimals enabled in the answer. But so what are your comments on this? Okay, so the point is, if at all you want to, so you still choose the nearest answer, and then in the last comment section you mentioned that for this I have chosen the nearest answer. Yes. Hmm. So we are one question is in waiting, so we'll go to that first, and then we'll come back. So here the question number was 15. Okay, I think Uh, 77.4. I think I looked at it yesterday. So let me quickly do it. I think, see, the question is DC shunt motor. So let me, I don't have to keep switching the tabs. So this is the question number 15 that I'm trying now. So let's come to a new page and let's try blue this time. So the question was DC shunt motor. So let me quickly again see, for everything you make a drawing, it helps. So this is the armature resistance and this is the motor. So because it is a motor, it will have electrical input, 200 volt. So let me change the colors. 0.75, 295, 3.1 amperes. Light load. Okay, so light load, that means no load. See, first I'm taking the case of no load condition. So, from what I could remember, we need to find the rotational losses for this. So, uh, here it is 200 volts, right? So, I can find this current. So, that is, so shunt field current is voltage by resistance. So, 200 divided by 295. Yeah, sorry. 200 divided by 295 is, yeah, 0.678 amperes. Okay. So this is the field current or shunt field current, 678. So now 3.1 is coming here, 678 is going there. So remaining will come here, 2.42, right? Okay, so then from this I can find the copper loss, PCU copper loss will be 0.678 square multiplied by 295 plus 2.42 multiplied by 75. So what is that? 678 square 295 plus 2.42 square 0.75. So is it 134 watts? That's what my calculator is saying. Okay. Okay, so this is the copper loss. So what is the total input? Total input is 200 is giving 3.1. Okay, so the total electrical input will be 200 into 3.1. So that will be what? 200 into 3.1. 620 watts. So this is under no load conditions. So the difference between these two, so the copper loss, if you remove from the electrical input, you will get the mechanical loss because the output is zero because it is in no load. Okay? So the entire is in the mechanical loss. So P rotational plus friction, whatever rotational loss, 620 minus 134. So that will be 486 watts. Okay. So now we go back to the question. So which says when the machine, what is the machine efficiency as a motor with input of 12 kilowatt at rated speed and voltage. Okay. So now the input is 12 kilowatt. So So now no longer it is on no load. It is now, I'll just change the color. Okay. So, or let me make a place. How do I select and delete? No, that is just text. Anyway, I will write it here. So with input of P input is 12 kilowatt. So that means I will be divided by 200, right? So 12,000 divided by 200, 60 amperes. Okay, so now the current increased to 60 amperes. So this current will be same. So therefore this will be 60 minus that. So PIIA armature current will be 60 minus to 0.678. Okay. So that is 59.32 amperes. So now the copper loss, yeah, it should be 140. So where is the mistake? Is the current value different? Let us check once again. 0.678 square into 295 plus 2.42 square into 0.75. Sorry, 140. 139.99 it is saying. So it should be 140. So if this is 140, then this is 140, then this will be 480. Okay, thanks. Meanwhile, here I got current here. So now I can find the copper loss. Okay, how do I find the copper loss? So simply again, this part will be same, whereas this part will be different. So I'll just change the current value, 59.32. So I'm getting 2775. Okay, round off. Okay. So again, you can see here the input is 12,000. From 12,000, 2,700 is copper losses. Okay. And 480 is the rotational losses. So the total output I'll get. Okay. So what is the output now? So output P out is nothing but 12,000 minus 2775 minus 480. Okay. So the total output will be here. So 12,000 minus 2775 minus 480. So 8745 is the output. So now I have output and input. So I can find the efficiency. So efficiency divided by 12,000. 72.87%. Okay, so that is the final answer. So let us check whether this 72.87 available in the options. So this one D is the answer. Okay. So the question is correct. Yeah. 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 Okay. So the question is, see, when the initially when it is operating at no load, so here you can see when it's operating at no load, the current will be taken less because the more you load the motor, the more current it starts pulling. So I have increased the output so such that the slowly current started increasing. So and since it is given input power is 12 kilowatt and the voltage is maintained at 200, so obviously current has to be 60 because power is current into voltage. Yes, yes. So if I the copper losses also again two types. So there is a copper loss in the armature, there is a copper loss in the shunt field winding. This will not change, whereas this will change. So So now if I go back to one of the previous drawings, okay. So this is reverse. We are talking. No, this is generator. Okay. So let's see motor if I have done. Okay. So there's no diagram for motor. So let's uh, anyway, motor or the generator both are same. So here input is 1370. This one is a mechanical input. From that rotational losses are removed. Then it is converted to electrical, which is eg into ia. From that electrical, copper losses are removed. That is 1309. From that copper losses, 709 is variable and 600 is fixed. So this fixed one and this fixed one both are added. So total fixed loss is like this. So this is the uh, older one. I think we have time to take one or two more questions. So let's quickly jump to one more question. So yeah, you can. Somebody, yeah, what? Yeah, what is the doubt? It's a question itself. Okay, so let's finish that. Yeah, in the same. Okay, so different paper. Okay, sorry, I have to search in my drive. Yeah, so what is the? Huh? GJP. Okay, I think that should be enough. Yeah. So this is again an interesting question. Actually, I wanted to build driven kind of thing is that. So what you did, what you ignored? Okay, okay, okay. So yeah, so you have to get the answer because see what the criteria what I used was I received some responses, right? Doubts. If any question has been asked by many people, that means that the question has a problem. But only few people asked it out, then yeah. Anyway, we can get the answer. Yeah. What is? Huh. So you can leave it empty, or you try to solve it, and then if you can find any closest option, you mention that. So see, the ignore questions are not for completely ignoring. You attempt the question, uh, but you don't expect the options will match. But at least you attempt the question, you will learn something from it. So see, the question did not make a mistake. The options are wrong. So don't trying to solve the question. Anyway, so let's quickly do this and then we'll go because this is something. There is a generator and motor. So when anything comes like this, both generator and operation and motor operation, so conceptually it is interesting. And this kind of questions can be asked in the interviews also. That okay, generator is running, suddenly somebody comes and the belt is broken. Then what happens? Okay, so I'll explain what is the meaning of that. So let's try this. So, question number 18, just to have a look at the question. We'll come back and answer it. So, the question is belt driven DC shunt generator. So let's draw that. See, shunt generator, right? So, it will have a shunt field winding, and this is the G is the generator. And because it is a generator, output will be electrical. So, there will be a resistance load which will take some current. And they are saying that some belt driven, that means some mechanical input is being sent into the generator where it converts to electrical and supplies to the load. So I will write the values. So 1420, so the speed is given to be 1420, 1420 rpm, delivering 7 kilowatt at 235 volt bus. Okay. So this the voltage here is 235, and it is delivering a load of 7 kilowatts. So I'll switch to a different color. The belt breaks, following which the machine operates as a motor. See, here there is an important word called a bus. Okay, so there is a bus means bus is used in electrical engineering. It means that it is like a bar where voltage is being maintained. Okay, so here the voltage is maintained at 235 volts. Okay, so now the question is there is a mechanical input going in. If the mechanical input stops, okay, then what happens? So no longer the mechanical input is coming. So the generator will stop generating, and meanwhile it is connected to a bus of 235 volts, right? So it will start current will reverse. It will start taking some current and it will start operating like a motor on no load. Okay? So it will start operating like a motor on no load. Uh, so see, this is on generator mode. Then so belt is broken. So then therefore motor operation. Then so now the input power is 1 kilowatt. So it used to generate 7 kilowatt, but now it is consuming 1 kilowatt. The armature and field resistances are given. So 0.24 ohms, and the field resistance is 52 ohms. The speed when working as the motor will be. So now I need to find the new speed. So now, first what we'll do, we'll consider the generator operation and find out the EG, EMF generated. Okay. So when it is working as a generator. So what is the EMF generated? Okay. So first 7 kilowatt 235. So what will be the current? It will be generating. So 235 7,000 divided by 235 will be the current. So 7,000 divided by 235, I get 29.8 amperes. Okay. So 29.8 amperes, the arrow will be towards the right side. Okay. So because it is a generator, it is generating. Now the field current will be, like this. So same voltage is known. So 235 volts V divided by R, 52 ohms. So I'll get current of 4.5 amperes. 4.52 amperes or something like this. So the current direction is this way. So now, because it is a generator, it has to generate both the currents. So the total current here will be the addition of these two. So plus 29.8, so which is 34.32. So now I calculated the armature current. So there will be voltage drop here, and the remaining voltage drop will be nothing but the EMF generated. So EMF generated is the drop IARA plus the terminal voltage. Okay, so that is 34.32 into 0.24 plus 235. Okay, so it will be more. So it is 243 volts. So the EMF generated is 243 volts, which this is EMF is generated because the speed was this speed is resulting in this voltage being generated. Okay. Now we are in the motoring mode. Okay. So now here again notice that there was no question about what are the losses, what was the efficiency. That's why we are not calculating all that. Okay. So now power in. Now we are. Let me make a small drawing again. So this part will be same, and then Okay, this is M, and now so this is 235 volts. The bus voltage is same. 1 kilowatt input power. So what will be the current? So thousand divided by 235, right? Power by voltage is current. So that is 1000 divided by 235. 4.2. Okay. So here is where we get the problem. So in that case, there is no current going in, so it is not possible. So here, what you can do, just for sake of completion, let us say input power is 2 kilowatt. Okay, so this current will double, so it will become 8.2000 divided by 235. So that is 8.5. Okay, so then 4.5 is here, so remaining 4 amperes is here. So the drop here will be uh, eb, back emf. Okay, so eg will be for emf generated in under motor operation. It will be like this. So 4 into 0.24. Okay, so this should be subtracted from 235. Okay, so what will that be? So 4 into 0.24. So 0.96. So 235 minus 0.96. So you round off to 234 is the back EMF. Now, in a DC machine, the EMF generated or the back EMF will be proportional to the speed, assuming that the field current is constant. Okay. So under field constant, so it will be like both like proportional. Okay. 1420 RPM gives 234 volts. Sorry, 243 volts. So then 234 volts should give how many RPM? So it is just cross multiply and you can find that. Okay? So that is 1420 multiplied by 234 divided by 243. 1367 RPM. Okay? So under motoring operation, speed is 1367. So here so finally to go back, I think see now what happens here, this constant which is there, right, 1 kilowatt power. Okay. Now, some other student might have got 2 kilowatt, so they will not raise any objection. So the people who are raising objection will be few in that case. So anyway, I'll try in my second round. I'll try to look at that. So if you find this kind of thing, you mention in the what do you call it, the final comments part of the submission. Okay. Yeah. So sorry we could not come to your question. Anyway, so we'll stop and then we'll continue outside. Just a minute.